The air in the Earth's atmosphere is also a fluid that exerts a higher pressure as the depth within it increases. In one sense, we are all living at the bottom of a sea of air that is the Earth's atmosphere. Similarly to a regular sea, as one goes deeper into the Earth's atmosphere, the pressure due to the weight of the air above increases. Hence, at an elevation of 48 kilometers above Earth, the atmospheric pressure is practically zero. And it increases as we go deeper into the Earth's atmosphere, until it reaches about 1 atmosphere at sea level. If one were to go lower than sea level, such as down a mining shaft that sinks into the crust of the Earth, one would experience a higher than atmospheric pressure. It should be noted that although a standard atmosphere is defined as 101,300 Pascal, the actual pressure at sea level at any given location and time can be slightly higher or lower than that value, depending on the temperature and weather conditions. A mining shaft extends for 1 kilometer beneath sea level. Assuming the density of the air within the mining shaft is the same as the density of air at standard atmospheric pressure and temperature, calculate the pressure at the bottom of the mining shaft. Does the assumption of constant density introduce an error into the pressure calculation? Explain your answer. Finally, if the mining shaft were flooded with water up to sea level, what would be the pressure at the bottom of the shaft? The standard atmospheric temperature is equal to 288 Kelvin. Using the ideal gas law, we can calculate the density of air at sea level as being equal to the atmospheric pressure divided by the gas constant for air times the standard atmospheric temperature of 288 Kelvin. So ρ air is 101300 divided by 287 times 288, which is equal to 1.22556 kilograms per meter cubed. We can then use this density value to calculate the pressure at the bottom of the 1 kilometer deep mine shaft, assuming constant air density. The pressure at the bottom of the mine is equal to the atmospheric pressure plus the air density times the gravitational acceleration times the depth beneath the Earth's surface. Substituting the values of all the variables: 101300 for the atmospheric pressure, 1.22556 for ρ air, 9.81 for g, and 1000 for h. We get that the pressure at the bottom of the mine is equal to 113.3227 kilopascal, or 1.119 atmospheres. The constant air pressure assumption does introduce errors into the pressure calculation, for two main reasons. Unlike liquids, air, being a gas, is compressible. Hence there is a large change in the density of air as a function of pressure. Furthermore, the ambient temperature increases by about 1 degree Celsius for every 100 meters of descent into the Earth. Hence the temperature at the bottom of that mine shaft will be around 298 Kelvin. If the mine were flooded with water, the pressure at the bottom of the mine would be equal to the atmospheric pressure plus the water density times the gravitational acceleration times the depth beneath the Earth's surface. Substituting the values of all the variables: 101300 for P atmosphere, 1000 for ρ water, 9.81 for G, and 1000 for H, we get that the pressure at the bottom of the water-flooded mine is equal to 9.9113 megapascal, or 97.841 atmospheres. Pascal's law states: for all points at the same absolute height, in a connected body of an incompressible fluid at rest, the fluid pressure is the same, even if additional pressure is applied on the fluid at some place. Consider the situation where we have a tank filled with a stationary incompressible fluid that has 3 vertical branches. Branch 1 is open to the atmosphere, and thus is subject to pressure P0. Branch 2 is also open to the atmosphere, and is subject to pressure P0, and is partially filled with a different, less dense, fluid. Finally, in branch 3, a piston is used to apply a certain amount of pressure, P3, to branch 3. According to Pascal's law, the pressure at points A, B and C, that are located in branches 1, 2 and 3, respectively, is the same. This is true since points A, B and C meet the 2 conditions set forth in Pascal's law for their pressures to be equal. They are all located at the same elevation, and they are all within a single connected body of liquid. In the shown tank, the pressure at points A, B and C is the same, according to Pascal's law. The pressure at point A is equal to the ambient pressure P0 plus the density of the higher density fluid times the gravitational acceleration times the height of the fluid in column 1. The pressure at point B is equal to the ambient pressure P0 plus the gravitational acceleration times the summation of the density of the higher density liquid times its height within column 2 and the density of the lower density liquid times its height within column 2. The pressure at point C is equal to the ambient pressure P0 plus the density of the higher density fluid times the gravitational acceleration times the height of the fluid in column 3 plus the pressure exerted by the piston on column 3, due to the weight of the piston. This pressure, P3, is equal to the mass of the piston times the gravitational acceleration divided by the surface area of the piston face that is in contact with the fluid. In the shown 2 columns, is the pressure at points A and B equal? How about the pressure at points C and D? Are they equal? Symbolically compute the value of P2 minus P1 and PC minus PD as a function of the heights h1, h2 and h3. Based on Pascal's law, the pressure at points A and B is the same, since they are both located at the same elevation, and they are both within the same connected body of fluid. Points C and D, however, although they are at the same elevation, they are not within the same connected body of fluid. Point D is in the blue fluid, which has density ρ, whereas point C is in the light green liquid, which has density ρ/2 and height h1 within column 2. Now let's calculate the difference in pressure between P2 and P1. We first need to determine the value of the pressure at points A and B. The pressure at point A is equal to P1 plus the density ρ times the gravitational acceleration g times h1 plus h3, which is the height of the liquid in column 1. The pressure at point B is equal to P2 plus ρ times g times h2 plus ρ/2 times g times h1. Setting Pa equal to Pb, we get P1 plus ρ times g times H1 plus H2 is equal to P2 plus rho times G times H2 plus rho over 2 times G times H1. Simplifying this expression, we get that P2 minus P1 is equal to rho times G times H1 over 2 plus H3 minus H2. Similarly to the way we obtained the value of P2 minus P1 in the previous section, we can calculate the value of Pc minus Pd, starting from the equation that states that the pressure at points A and B is the same. Pa can be written as being equal to the pressure at point D, Pd, plus the fluid's density, ρ, times the gravitational acceleration, g, times h1. Pb is equal to Pc plus the density of the lighter fluid, or ρ over 2, times g, times h1. We then set the equation for Pa equal to the equation for Pb. Then by reducing the resulting expression, we obtain that Pc minus Pd is equal to ρ over 2 times g times h1. Another statement of Pascal's law is as follows. A change in pressure that is applied to a stationary fluid that is within a container is transmitted without change to every point of the fluid, and to the walls of the container. This means that if the pressure at any point within a stationary connected fluid is increased, the pressure throughout the fluid will increase by the same amount, and vice versa. Consider the situation where we have a piston with a cross-sectional area A1 that is supporting a car. The total weight of the large piston and of the car on top of it is equal to F1. The piston operates on top of a container that is filled with a fluid with density ρ. The container is connected to another smaller piston that has a cross-sectional area A2 and a weight F2. Initially, the system is at equilibrium and is hence stationary. We consider points C and D that are located at the bottoms of columns 1 and 2 respectively. Since both points are at the same elevation and within the same connected body of fluid, the pressure at point C is equal to the pressure at point D. The pressure at point C is equal to the pressure that the car and piston are exerting above column 1, or P1, plus the pressure that the column of fluid above point C exerts, which is equal to the density of the fluid ρ, times the gravitational acceleration g, times the height of the fluid column above point C, or h1. P1 can also be written in terms of the force F1 that the piston and car exert, divided by the surface area of the bottom of piston 1 that is in contact with the fluid, or A1. Similarly, we can calculate the pressure at point D to be equal to the force exerted by the small piston, or F2, divided by A2, plus ρ, times G, times H2. We can then set the two expressions that we obtained for the pressure at points C and D equal to each other. The shown hydraulic system, as we have mentioned previously, is in equilibrium. If a man, with weight W, steps onto the smaller piston, this will increase the pressure that is acting on the smaller piston, and consequently the small piston will tend to move downwards, while the large piston moves upwards until a new equilibrium position is reached. To obtain the new equilibrium positions of the small and large pistons, we need to determine the distances that both pistons have moved, or delta x1 and delta x2. Using Pascal's law, we can still state that the pressure at points C and D is the same. We can then write the expressions for Pc and Pd similarly to what we did before. The shown equation takes into account the fact that the force acting on the small piston has increased by the weight of the man, or W, and that H1 has increased by delta x1, and H2 has decreased by delta x2. Since we assume the fluid is incompressible, then the total volume of fluid within the container remains constant. Hence, using conservation of volume, we can state that the increase in volume in column 1, or delta x1 times A1, is equal to the decrease in volume in column 2, or delta x2 times A2. We can then rearrange this expression to obtain an equation for delta x1 as a function of delta x2, A1 and A2. Substituting the delta x1 equation into the previously obtained pressure equation, we get the shown expression. By rearranging the terms, we can get the following expression for delta x2. Hydraulic power is used in numerous applications as a force multiplier, where a relatively small force can be used to generate a much larger one. One application is that of a braking system on a car. When a driver presses the brake pedal on a car, the brake fluid within a small diameter master cylinder is compressed. This causes the much larger slave cylinder that is connected to the brake pads to exert a high force on the car's brake disc, which tends to slow the tire's rotation. Let's watch this animation a few more times. Pay attention to the brake pads. See how they move slowly together to grip the brake disc. The pressure in a typical car brake system can reach about 10 megapascal, or about 100 atmospheres. Hydraulic power is also used to drive the actuator pistons of various machinery, such as earth-moving equipment. The control surfaces of many aircraft are also controlled using hydraulic actuators. The hydraulic pressure in these applications reaches about 30 megapascal, or about 300 atmospheres. Another application of hydraulic power is in hydraulic presses that are used in metal forming and cutting operations, and in test equipment that is used to measure the strength of material samples. In these applications, the hydraulic pressure can reach 1000 megapascal, or about 10,000 atmospheres.